Hello students, today we are going to discuss homogeneous linear differential equations of second and higher order with constant coefficients. Contents of today's topic, outsketch of presentation, is objectives and introduction and a differential operator and some of the properties and a general solution of second order homogeneous equations and linear dependence and independence and Wronskian determinant, and overall summary we will discuss today. Here objectives of this presentation, here differential operator and some of its properties and the concept of linear dependence and independence and its set of the functions defined in the interval, and compute that is a Wronskian determinant, it is a set of functions, and solutions of linear homogeneous differential equation of order n and with the constant coefficients and finding the general solutions. These are the objectives. And introduction of this topic is here linear differential equation of order n is here d to the power of n y by dx to the power of n plus a1 into y to the d to the power of n minus 1 y by dx to the power of n minus 1 plus a2 into dy to the power of n minus 2 d to the power of n minus 2 into y by dx to the power of n minus 2 plus so on plus an into y equal to b of x. That is equation 1. And here a1, a2, so on, an are the constants and b is the function of x in the interval defined I subset are equal to real number system. Here this kind of linear differential equation represented into the L of y equal to b of x. Here L of y is here left side term and b of x is the right side term. If we take into the left side term is equal to the differential equation is called as a homogeneous linear differential equation. If a right side term is considered in this linear differential equation, that is L of y equal to b of x, that is b of x is not equal to 0, it is called as a non-homogeneous linear differential equation. Now this is a overall idea about that. It is a given nth order linear differential equation, left side term will give that is a complementary solution and right side term is gives that is a particular integral, finding of the general solution. Here particular differential equation, here b of x is equal to 0 homogeneous, b of x is not equal to 0, it is a non-homogeneous differential equation. Now here differential operators of the sum of its properties, it is clearly operators means it is a d by dx is represented as a d, and d square y by dx square is represented as a d square, and d cube y by dx cube equal to capital D cube. Like it is a representation d power n by dx to the power of n equal to it is a d power n. So this is a capital D power n. These are the representation or terms are called as a operator. Capital D is called as a operator. In this differential equations, here we can substitute here dy equal to dy by dx and d square y equal to d square y by dx square, so on d power n y equal to d power n y by dx to the power of n. Here d is called as a operator in the differential equation. Now here generalization, it is a differential, it is a y power n. Y power n means yn means it is a d power n y by dx to the power of n, that is represented as a d power n into y. So here the left sided term is called as a total function is called as a operator function, that is f of d equal to d power n plus a1 into d power n minus 1 plus a2 into d power n minus 2 plus so on plus an. This is f of d into y, it is a representation of here homogeneous linear differential equation left side term. Now it is a case of f b of x equal to 0. It is called as a homogeneous linear differential equation. So that it is a, we have in our syllabus today here discussing that is a homogeneous linear differential equation. Example is if I take into the differential equation d square y by dx square plus 4 minus 4 into dy by dx plus 2y equal to 0. I want to convert into the operator form. Here d by dx is I will write d. So first term is d square y and second term is minus 4dy plus 2y equal to 0. So that is why we take the common d square minus 4d plus 2 into y equal to 0. Here f of d equal to d square minus 4d plus 2 is called as a operator function. It is order 2. That is a homogeneous equation, linear homogeneous differential equation operator 2, differential equation order 2. Now here b of x is not equal to 0, that is called as a non-homogeneous equation. It is a example if I take 5 into d square y by dx square plus 3 into dy by dx plus minus 4y equal to sin 2x, because of right side term is a sin 2x, so that it is a 5d square y plus 3dy minus 4y equal to sin 2x. It is taking into the common y, it is a 5d square plus 3d minus 4 into y equal to sin 2x. Here operator function f of d equal to 5d square plus 3d minus 4. Now it is some elementary operators properties of the differential equation, differential operators. If I observe here, some of the two operators of the functions f of d plus g of d into y equal to, we can separate f of d into y plus g of d into y. It is a differential terms. Whenever we want to be separate, we can be separate. Any second one is a second property is here, if we have that is a function multiples with the any constant k into f of d into y equal to k of f of d into y. Now it is taking the product of the two operators, it is a differential operators. If I take f of d into g of d into y equal to f of d into g of d of y. So it is a first we complete that is a g of d into y, then after we can go for f of d into f of d operator. Then it is sometimes it is a commutative property also clearly satisfies in the operators. It is f of d plus g of d equal to g of d plus f of d. Another is a product also it satisfies f of d into g of d equal to g of d into f of d. These are the four properties. Another fifth property comes to the here he will ask that is a prove that it is f of d equal to d power n plus a1 into d power n minus 1 plus so on plus an. This is a operator. It is a f of d into e to the power of m. If we multiply, that is a f of m into e to the power of mx. That is a m is a constant that we want to be prove it. So it is operator will be there. If we multiply with the function e to the power of mx, then it is clearly up to derivative after that function value f of m into e to the power of mx. That is the formula. Now proof point of view, I will take d of e to the power of m x. It is called as a d by dx of e to the power of mx. So it is m into e to the power of mx. That is the first derivative of the function. Again I will take that is a d square into e to the power of mx, d into d of e to the power of mx. So here d of e to the power of mx equal to d by dx of m into e to the power of m square into e to the power of mx. So on continuation it go for the d power k into e to the power of mx is m to the power of k into the power of mx. It is continuation of that. It is f of d into e to the power of mx. E to the power of mx, it is each term if we apply the total function f of m into e to the power of mx. This is hence it is proved. Now property number 6, it is comes to the f of m equal to 0, y equal to e to the power of mx is the solution of f of d equal to y equal to 0. So that here we can take f of d into e to the power of mx, it is clearly we can represent f of m1 into e to the power of m1 of x. So here 0 it is equal to 0. So e to the power of m1x satisfies, so that it is a f of d into y equal to 0. So solution is clearly we can say y equal to e to the power of m1 of x is it is the solution of f of d into y equal to 0. Hence it is proved for the property 6. Next property 7 is it is the same similar manner of the property 5. It is f of d into d to the power of n plus a1 into d to the power of n minus 1 plus so on an. It is a where a1 a2 so on an is a constants. Then here we want to prove that e to the power of m x into f of d into y equal to f of d minus m into e to the power of m into y. So here first we prove that it is a right side term. I will take f of d minus m into e to the power of m x into y equal to, it is the differentiation of e to the power of my minus m into e to the power of my mx into y. So separating the terms, and derivative first term we have and second term as it is. So that derivative operations if we apply e to the power of mx into dy. So similarly it is a d minus m into whole square e to the power of mx into y. So that d minus m into d minus m into e to the power of mx into y. So similarly we can take that it is up to n terms, it is a d minus m whole to the power of n into e to the power of mx into y equal to e to the power of mx into d power n into y. So that is hence it is proved for the property number 7. Now here continuation, if I take that f of functions, if we apply f of d minus m, it is hence it is we can be separating the terms and we can apply, so that function f of d into y coefficient is comes to the e to the power of mx. So it is a right hand term, if we take it is a left hand term, we got it. So e to the power of mx into f of d into y equal to f of d minus m into e to the power of mx into y, hence it is proved. Now it is a eighth property comes to the pi of d square equal to d square whole to the power of n plus a1 into d square whole to the power of n minus 2 plus so on an. Here whenever the function is comes to the sum sin mx and cos mx, such a moment here d square equal to minus m square we can be substitute. That is a property number 8. So here I will take the differentiation of sin mx, proof point of view, m into cos mx. Here similarly it is go for the d square into sin mx, means it is a again m into cos mx. About the differentiation of sin mx is a m into cos mx. Now again we go for the differentiation of m into cos mx, it is a again it is a m square minus m square into cos mx. Then it is going for the continuation of the derivatives. Here cos mx derivative is how much? Minus m into sin mx. So minus m square into sin mx, that is the derivative of the 2 d square. Continuation d cube and d power 4 so on d power k. Continuation if we go for that d square whole to the power of n. Sin mx minus m square into whole power n into sin mx for all it is n equal to 1 to so on. Hence it is proved. So that it is a pi of d square if we take that is a function of term and sin mx. So continuation it comes to the here pi of d square sin to the power of sin mx equal to pi of minus m square into sin mx. So this is similarly we can prove that pi of d square into cos mx equal to pi of minus m square into cos mx. Next, general solution of the second order homogeneous linear differential equations. That is left side homogeneous means right side b of x equal to 0. So here left side term L of y equal to f of d into y equal to 0. So L of y means left side term I will take homogeneous second order equation d square y by dx square plus a1 into dy by dx plus a1 plus a2 into y equal to 0. Now here if I take d equal to d by dx operator, d square equal to d square by dx square, then it is operator form I will get d square plus a1 into d plus a2 into y equal to 0. So it is a left side term f of d into y equal to 0. That is equation 1 is converted into the operator form, we got it to the equation number 2. Now it is a auxiliary equation form. If I write it is instead of d we will substitute m. So it is m square plus a1 m plus a2 equal to 0. Now solving of these roots, here I will get that it is clearly it is a minus b plus or minus square root of b square minus 4ac by 2a. So that I will get the roots. Here b square minus 4ac is greater than 0. Now I will get the m1 m2 are the real and distinct, and b square minus 4ac equal to 0 real and equal, that is the roots, and m1 m2 it is a less than 0, it is called as a complex conjugate complex roots. So that it is a depends on the roots we can obtain the solution. So here first case is comes to the here all the roots are real and distinct. There it is a solution y equal to c1 into e to the power of m1x. Here m1 m2 so on mn are real and distinct. So that y equal to c1 into e to the power of m1x. That is the first root solution plus second root solution c2 into e to the power of m2x plus so on plus cn into e to the power of mnx. Now it is a roots are real and equal. That is a case 2 m1 equal to m2. So that it is a we can take here c1x plus c2 into e to the power of m1x because of here m1 is a equal for the m1 and m2. So that it is any continuation m3 and will be there c3 into e to the power of m3x plus so on. How many n is there cn into e to the power of mnx. So this is a whenever the roots are real and equal. If I take that is a 3 roots are the equal m1 equal to m2 equal to m3 in the case 2, then it is a y equal to c1 into x square plus c2 x plus c3 c2x plus c3 into e to the power of m1x. Because of 3 roots are equal, 3 constants we have c1 c2 c3 with coefficients, then it is a c1 x square plus c2 x plus c3 into e to the power of m1x. Remaining is a distance, so that separating of the separating solutions we can write it is a c4 e power m4x plus so on. Now it is a coming to the roots are complex. Complex means it is a minus b plus or minus a plus or minus I b, otherwise alpha plus or minus I beta. Then we can go for that solution is e power a alpha x into c1 cos beta x plus c2 sin beta x. That is a complex roots. Here whichever it is a 3 kind of the roots we can get, so that it is each case we can obtain the solution. Now here this is a roots are real and distinct. It is a table clearly explain that it is a roots are real and distinct. It is a roots are equal, roots are complex. Such kind of it is a complementary solution we can write. Now here example I am taking for this linear differential homogeneous linear differential equation solutions. It is a second order if I take d square y by dx square minus 5 dy by dx minus plus 4y equal to 0. Here we write into complementary function. It is a m square minus 5m plus 4 equal to 0. Here instead of m I am taking r. So r square minus 5r plus r plus 4 equal to 0. If I find that is the roots, it is a m1 equal to 1 and m2 equal to 4. That is r1 equal to 1, r2 equal to 4. So that here 2, so directly I can write the solution y equal to c1 e to the power of x plus m1 equal to how much? 1. So c1 e to the power of 1 into x plus c2 e to the power of 4 into x. This is a general solution for the homogeneous linear differential equation. Coming to the second example, it is a d square y by dx square plus 2 into dy by dx plus y equal to 0. This is the operator form I can write. It is a r square plus 2r plus 1 equal to 0. This we can write as a r plus 1 whole square equal to 0, r equal to minus 1 and minus 1, 2 roots are equal. So it is a c1 e to the power of minus x plus c2 x into e to the power of minus x. These are the general solution. That is a only complementary solution we can get. So that it is a, because of right side it is a particular integral is a 0. So that it is only left side term is comes to the general. So general solution is equal to the complementary solution plus particular integral. So that here we got it only the complementary solution, particular integral is 0, no need to take. So it is a y equal to general solution c1 e power minus x plus c2 x into e to the power of minus x. because of it is the roots are real and equal. Now coming to the roots are complex. D square y by dx square plus 2 into dy by dx plus 5y equal to 0. Here auxiliary equation is r square plus 2r plus 5 equal to 0. Here complex roots I will get minus 1 plus r minus 2i. So that here minus 1 is alpha and beta equal to 2. So that directly we can write C1 into e to the power of minus x into cos 2x plus sin 2x. Separating the terms in the general solution, y equal to C1 e to the power of minus x into cos 2x plus C2 e to the power of minus x into sin 2x. This is roots are complex. Now it is linear dependence. Linear dependent means it is a C1 pi of x plus C2 pi 2 of x equal to 0. C1 pi 1 plus C2 pi 2 equal to 0. Here that kind of the solution is called as a solution we obtain. Now it is a function pi 1 and pi 2 are the linear dependent or independent that I want to say. Here linear dependent and independent finding of that, it is a C1 C2 both are not the equal, not the 0. Here C1 C2 are not the 0, then it is a linear dependent. That is we can see in the bracket I kept. Here linear independent. Linear independent means it is a C1 pi 1 of x plus C2 pi 2 of x equal to 0. Here C1 equal to C2 equal to 0. Both are the 0. Then it is a linearly independent. That is a linear dependent means it is a functions are the pi 1 pi 2s are the zeros, but C1 C2s are not the zeros. It is a C1 C2 both the total is it is become 0, but C1 C2s are not 0, but total equation is the left side term is equal to 0. Pi 1 pi 2s are the functions, that is a linear dependence. A linear independent means it is a here C1 and C2 are 0 and pi 1 of x and pi 2 of x is non-zero functions, then it is a linearly independent. Now here example, if I take pi of x equal to e to the power of some m1x plus c2 pi to x e to the power of n to x. Now it is a clearly if we go for that, it is a p of x equal to auxiliary equation here r square plus a1r plus a2, then it is a linear differential equation y double dash plus a1 y dash plus a2 y equal to 0. It is a linearly independent. So here he is asking to prove that. So that it is a solution I can write c1 e to the power of m1x plus c2 e to the power of m2x equal to 0. Now here C1 e to the power of m1x plus C2 e to the power of m2x equal to 0. Now it is we go for the differentiating, it is C2 R2 minus R1 e to the power of R2 minus R1 x equal to 0. Now here m2 minus m1 x R1 R2. Now it is comes to the it is not equal to 0. Therefore it is clearly C1 equal to 0 and C2 equal to 0. Therefore we can decide it is a linearly independent, hence it is proved. Now it is a Wronskian determinant. Pi 1 of x and pi 2 of x are the any two solutions. It is a Wronskian determinant means W of pi 1 comma pi 2. This determinant is we can identify pi 1 pi 2s are the two functions and pi 1 dash pi 2 dash is a another derivative of the functions. If we take it is a whole determinant is pi 1 pi 2 dash minus pi 2 pi 1 dash. Pi 1 dash pi 2 dash are the derivatives. So it is a pi 1 pi 2s of the solutions of the differential equation L of y equal to y double dash plus a1 y dash plus a2 y equal to 0. Then Wronskian determinant W1 of pi 1 pi 2 is clearly W of a pi 1 comma pi 2 is a determinant of pi 1 pi 2 pi 1 dash and pi 2 dash, it is a determinant we can identify AD minus BC form. So it is a determinant is a not equal to 0. Directly we can conclude that it is a linearly independent. And the determinant is equal to 0, then pi 1 pi 2s are the linearly dependent. So here previously directly based on the C1 C2 we can decide, here we can decide by using the Wronskian determinant with the functions phi 1 and pi 2. Now here example, if I take here pi 1x and pi 2x, pi 1x equal to cos x, pi 2x equal to sin x. Here pi 1x is another example, pi 1x equal to cos x, pi 2x equal to 3 e to the power of function, exponential function if I take. Now a first example, it is a here function is I can write c1 cos x plus c2 sin x. Now differentiation I will take and determinant form cos x and sin x and minus sin x and cos x. Here determinant form I can be used and directly solving of these equations I can be used. So that finally I will get c1 equal to 0 and C2 also 0, therefore linearly independent. Now similarly I will use that is a second equation. The second equation also the C1 cos x, C1 into pi 1x plus C2 pi 2x equal to 0. Now I will take the differentiation and both here I will solve, then C1 C2s are not equal to 0. So it is I can decide it is a linearly dependent. Here summary of this lesson, if I go further, it is here differential operators and its properties. Here it is most important, here operators, some of the operators, here left side term f of d equal d into y equal to 0. So f of d is called as a operator. That operator, so how we will be used in that it can be that we learned into the properties. Here different kind of the functions, different kind of the linear differential equation is there. So operators are the based on the order and degree that we will be decide for that it is a differentiation, so how we can be use that particular order. Here we are using the linear differential equation, so that it is order is degree is 1 and degree is 1 and order we are take that is a second order or third order, so that we are different kind of operators we are using here. And linearly dependence and linearly independence here depends on the Wronskian determinant we can be identify, number 1, and Wronskian determinant it is not equal to 0 linearly independent, equal to 0 linearly dependent. That is instead of that it is a linearly dependence case and a linear independent case, it is a constants of the functions even pi 1 of x plus c2 pi 2 of x equal to 0. It is a functions based on that also we can be identify. That is a interlink with the linearly dependence independence, and instead of these two calculations we can be used that is a Wronskian determinant. That is the most important aspect. Another is a homogeneous differential equations of order n and constant coefficients finding the general solution. Here whenever that is a right side term b of x equal to 0, then we are using that is a homogeneous linear differential equation. Here homogeneous linear differential equations f of d into y equal to 0 left time, that is whenever we are converting to the auxiliary equations sometimes it is a order is a more than 2. So it is a third order linear homogeneous differential equation and fourth order homogeneous linear differential equation. Such a type of cases we have to be used that it is a particularly synthetic methods we will be apply. From the synthetic methods or for calculation of the roots we can be identify the roots. That is by using that is a complementary solution. But so for the purpose of complementary solutions we can identify the roots. First it is a synthetic method, means by using the substitution method. By using the substitution method we can identify the roots. First root by substitution we can identify one root, then we can go for that is a synthetic applying that it is a conversion to the second order. From the second order we can use a minus b plus or minus square root of b square minus 4ac by 2a, so that we can identify the solution. This is a overall idea about that. It is whenever the order is more than 2, it is a homogeneous differential equations of order is n with the constant coefficients. Now here in this case it is a y equal to e to the power of m1x we are using the solution. Here f of d equal to nth order differential equation d power n plus a1 into d power n minus 1 plus 1 a n, it is a a1 a2 so on the n the constants. Here whenever we want to be the functions directly, here I want to identify the solution, means here directly there I can be use the solution f of d into e to the power of mx, means it is a functions directly I can substitute f of m into e to the power of mx. It is also one of the properties, is the most important property. Here first order derivative is a d into e to the power of mx, if we use it is a differentiation m into e to the power of mx. Similarly it is go for that, similarly up to it is a derivatives I can use d power n e to the power of mx, means it is a m power n e to the power of mx. Now it is go for that is the substitution of the function. Operator form we have to be used f of d into e to the power of mx. So operator form what is that? It is a d power n plus a1 into d power n minus 1 plus so on a plus an, that is right side, into e to the power of mx. So it is a each term going of that, it is a total, it is a derivatives after that getting of the function is called as a functional value f of m. That we have to be get it. We will get into the simplification part. That is known as it is a most important property for that. It is f of d into e to the power of mx equal to f of m into e to the power of mx. It is not directly substitution. It is separately. It is each term we should be multiply. Then after each derivative, then function it is after each term it is a 2 d square means 2 times take the derivative. D cube means 3 times take the derivative. Up to n times means it is n times we should take the derivative for the each separation of the term. After that it is whichever the term e to the power of mx we have, that we will take the common, so that we have to be get the functional value f of m into e to the power of mx. This is a property number 5 is most important. Then we can go for that, it is e to the power of m into f of d into y equal to f of d minus m into e to the power of mx into y. So here in this case similar manner we can apply the phi, that it is a d minus m into e to the power of my. Whenever we have to e to the power of mx into y, we have that we will be separate the terms, and here also we should go for that the derivative e to the power of mx into dy by d. Here u into v formula we should be apply. That is e to the power of mx into y is e to the power of mx into dy by dx plus y into d by dx of e to the power of mx. So that there it is the second term is as it is minus m into e to the power of mx into y. Here first term is e to the power of mx into dy plus m into y into e to the power of mx. So that it is a e to the power of last two terms, it is a m into y e to the power of mx minus m into y into e to the power of mx, both are cancelled, so that e to the power of m into dy. So particularly here function e to the power of m e to the power of mx into y, then only we can be use this operator, and finally it is a simplification we get, it is e to the power of m into d into y. So here going further is the second time derivative, d minus m whole square into e to the power of mx into y equal to d minus m into d minus m into e to the power of mx y. Already first derivative you got it, e to the power of mx into d into y. So again we should be apply that same simplification, it is the last two terms will be cancelled, that we should be observe here, and the first term will be e to the power of mx into d square into y, that we can be get it. That is a logic behind this, it is a unit v, when we will apply the term here, separation term, it is a second term, what we have as a derivative y into e dy by dx of e to the power of mx, and the last term both will be the cancel. That's why it is only first term we obtained, so that d minus m whole power n into d power m into y e to the equal to e to the power of mx into d power n into y. So that is a simplification part. Here functional observation if we come, f of d minus m into e to the power of mx into y. So here e to the power of mx into y, that is each term we should be go for the separation. So d minus m into whole power n into e to the power of mx into y plus a1 into d minus m whole power n minus 1 into e to the power of mx into y, plus so on, plus last term a into e to the power of mx into y. Here first term simplification I got it e to the power of mx into d power n into y. Second term simplification a1 into d power n minus 1 into y into e to the power of mx, plus so on, last term e to the power of m into e to the power of an into e to the power of mx into y. Now e to the power of mx into mx is, if we take the common, it is a total will come to the f of d operator form into y. So that it is a e to the power of mx into f of d into y, we can write as a f of d minus m into e to the power of mx into y. So this is a separation of the form, so that it is a first term, what are the cancellation we have, that we should be observed, and second term it is also derivative forms also, last two terms will be cancelled, and up to going of that it is a last up to nth term derivative, last two terms are the cancelled, so that e power mx into d power into y. After that here we will go for that f of d minus m e to the power of mx into y, then we can get that is e to the power of mx into f of d into y. This is a overall idea about this property, this is the most important property. Now it is a whenever we have to sin mx, their derivatives also we have to be apply the same process, and a generalization, general solution means it is a complementary solution and particular integral. Right side term is a we have, then it is a particular integral, only homogeneous differential equation, left side term only we will be used, so that it is a f of d into y equal to 0, so that complementary function it is a f of m equal to 0, that gives that is a roots, then we can be apply that is a solutions. So this is a overall idea, it is a complementary solution is called as a general solution. General solution means it is a complementary solution. Now here based on the roots we can obtain the different methods, it's the roots are real and distant, roots are real and equal, roots are complex. Then we can be apply these formulas such a way we can identify the, these are the problems we can be apply. This is a overall summary about that. It is a linear dependence and independence case, it is a, we should be remember linear dependence means C1 C2 is not the both are 0 whenever the function is C1 pi 1 x plus C2 pi 2 x equal to 0. When linearly dependence means it is a C1 pi 1 x plus C2 pi 2 x equal to 0, C1 equal to C2 equal to 0, then it is called as a linearly independent. Linearly independent case and dependent case, directly it is a based on that, it is a first derivative C1 pi 1 x plus C2 pi 2 x equal to 0, first derivative we can apply, then both we will be solved, then we can be get that C1 C2s. C1 C2s are not the both are zeros, then it is a linearly dependent, both are the equal to linearly independent. Now it is a, this we can be checked by that is a Wronskian determinant. Wronskian determinant is a not equal to 0, the linearly independent, Wronskian determinant equal to 0, linearly dependent. This is a overall summary for that. These are the examples generally we will be applying. Thank you.